Well, thank you very much. I'm supposed to talk about anti-colony today. And the question is, what kind of anti-colony I'm talking about? Actually, I will talk about anti-colony of the software. And because of the big data, the software and information processing is critically important. You know, the anti-colony actually, the ants are actually emerging to create the infrastructure for them to live and do things. And the software is the anti-colony of the biomedical and systems biomedicine. And so Garuda Platform, as in title today, is the software platform that I have been building for last 5 years with the community of not the ant, but the distinguished researchers institution around the world, and are now actually coming to the public release. Now, when we talk about this big data, one of the major revolutions in the biomedicine now is in how you actually connect your mutations or like a genome to the physiology. Therefore, you can make a proper decisions in a diagnosis and a therapeutic decision. For example, in a cancer, not just like a lung cancer or breast cancer, the question now is what kind of mutation that each cancer cell have, what kind of what set of mutation, not just one, have. Therefore, which group of patient are you belonging to? Therefore, what is the most effective treatment? And a simple correlation between the mutations and the patient cohort has been easy, but I think it's not that easy because the system is complex. Therefore, we need to look into systems property, which is basically the network, the molecule, network, the gene regulations to make better sense, have a better predictions capability. And so the system property is going to be very important. Now there's a lot of effort, including the one actually global effort, virtual humans, stem from this virtual hepatitis project with the German project, which I was one of the advisor and reviewer for many years, and also a virtual physiological human project, which is the EU project. Also, we have a Japanese counterpart of the HD physiology project, and there are many projects which is trying to establish the very precise organ model and a whole body model, which actually can have the reasonable simulation of the human pathology and the molecular interaction in computer. Now, but this is actually the moonshot in a way. You know, it requires a quite substantial set of science and set of engineering. In a moonshot, you need a set of key factors. One, you need the visions. Second, you need the principle, how you get to the moon. In Apollo project, it was a planetary flyby that actually had guaranteed that we can get to the moon in a specific orbitary projections. And we need engineering platform. But you see is a platform launch vehicle, which is Saturn V. And that is a very good piece of engineering that enables scientific missions. And we, of course, need the teamwork. So those four factors have been critical for Apollo missions. In rocket science, these are important. And the systems biology and systems biomedicine challenge is no exceptions. I think Professor Lee Hood, we're going to talk about how people medicine will transform the biomedicine, actually, which is about like a vision and a principle, and how we're going to carry out scientific discovery, for example, in exploration on the moon. But I'd like to focus on this lower bottom part, which is the engineering platform and teamwork, how we get to the moon. Now, the critical part actually the software and data resources. Now, software and data resources biomedical is so important, but it's so diverse and so extensive. And the reality is no one can build the entire software and database alone. And no country will be able to build them all. And we need the collaboration. At the same time, the reality is they are developed rather independently, or really quite independently, and the result is actually a lot of mess. And different interface, different program interface, and need to launch to independently, and then talk to each other, and no direct data sharing. And that's the reality of biomedical software today. So like interoperability of data resource and software is pretty missing, and so the researchers have to spend a lot of time working and fix those problems by themselves, which is not what they're supposed to be doing. The solution is we need open-ended integrated software platform, which actually, this is a kind of a paper we published 2011. If you want to go into detail, you want to actually take a look at this. And so like, we need the platform, not just the tools, but we need the interoperable platform, enable the open-ended software innovations into the integrated form. And so like an integrated platform, it's drive the industry. if you look at this publishing industry, for example, Adobe Creative Suite, which is a group of software that's integrated. Or music industry, there are a lot of software that's connecting each other. That's why the music industry is very efficient now. Or even airlines like Star Alliance, Lufthansa, All Nippon Airs, and United actually has been independent, but they have the same platform. They code sharing, same reservation system. So we can actually fly very easily and make decision where to fly and what flight to take. This capability of the high interoperability is unfortunately not sufficient in biomedical software and data. So therefore, we create the platform, the Garuda Platform, and we connect biology. So the Garuda architecture is open-ended architecture. Not just like a commercial vendors, also the academic institution, they create software. As far as they comply with the standard we said, like an API, relatively flex open standard, they can talk to each other. We provide a downloading side. We provide a core platform, and then software can talk to each other, and the user will be one shot. We provide a one-shot service. So the developer-wise, you don't have to worry about interoperability. As far as you comply with the Garuda API, your software is guaranteed to interface with other software which other institution might create it or other commercial vendor might create it. And for the user side, if you come to the Garuda side and the downloading side, you can download the software that all talk to each other. So this is really the benefit of the developers, benefit of the users, and this has been relatively missing. And this is the Garuda website. This is the Alliance website. The public release is now ready, and you can download public beta release, and we're actually doing quite a bit of improvement for the official release by the end of the year. And for the academic and then most corporate researchers, this is for free, and we're actually trying to get the enterprise service because the corporate have a specific security concern. So we actually have built a corporate version, which actually the launch customer is Takeda Pharmaceutical in Japan. Now, so this is the collaborations on not the ant, but distinguished researchers. So just to name a few research institutions like EMBL, A-Star from the Singapore, and Riken from Japan. And those this is only a short list of the icons, but we have an increasing number of academic and commercial vendors who's interested. Also, we are in discussion with the FDA and the IMI and then the Transplant Foundation to actually integrate with some of the software and the clinical database, which they consider to be very important. And so this is the gateway that you can actually download. This is kind of a snapshot, and then you can actually download software with a choice. And then as far as software being downloaded from this site, the API, the Garuda system enable each software to talk to each other, which was not really possible before. You have to do a lot of tricks to actually for each software to talk to each other. Now, this is a little short video that actually enable you to see. Can you actually play this video now? Yeah, okay, yeah. So this is, for example, like a booting, one of the software which we developed called the Cell Designer, which is talking a very detailed molecular interaction. What you saw just in front is a dashboard, which actually connecting software each other. Now you're actually going to boot this literature mining system that enable you to actually search the literature of the interest. With because you're actually looking into some of the molecular interaction, the system already knew what literature you are looking into, you're searching for. You don't have to type in the name of the molecule or name of gene, because what you're doing is contextual sensitive that the system knew what you're interested. Now actually some of the literature is in a list, and you can click and you go to the PubMed, and you can actually download and browse through those papers as well. Now, also, in the background, a lot of processing going on. One of the processes now connecting to Wolfram Alpha. Now you can see the kind of physical positions and the splicing pattern of the genome, a gene that you are interested. Also, this is the context sensitive from system understand from the tracking what you're doing, and the system can tell you, okay, this is what you're interested in, and automatically give you the feedback. Also, this is actually context sensitive literature. Google Images and the patent survey that they can automatically feed you depends on what sensing what you may be most interested. Now, so there are a lot of software. This is a kind of initial set software, but if anyone create a new software, new functionality, you can simply download and you can actually add the functionality. So this is a really open-ended system, and this is a versatile open-ended system. Now. Okay, so I think it's after this literature survey, actually, this user is interested in finding out a bit more on the molecular interactions, that where and then how things is connected. For example, this is the EGF pathway, which is very important in the cancer. Now, from this receptor to somewhere down in the molecule, for example, like some transcription factor, is there any pathway which is connecting this? So this actually give you all the pathway traversal and find out what are the route. This is like a Google map and try to navigate you the pathway, for example. In a very complex molecular interaction map, automatic navigation and guiding will be very important. You have like a lot of analytics tool. What are the intensity and what is the dynamics of those pathway, and those features. Okay, so some of the use case actually, I'm going to show you two use cases. One is the multi-scale integrations. This is one of the Japanese national project in HD physiology. Is create the whole body ADME PK model combined with the vertical integration of the heart model. So in this simulations, we use all the Garuda softwares, and so it's work as an integrated part. And then have the ADME PK model, which is designed by the physio designer, one of the Garuda compliant tool, and intercellular dynamics by cell designer, and the very high definitions molecular dynamic simulators, and then the whole body heart simulation by the physio designer. So like this is several layers. Like a molecular interaction, you see very detailed simulation. Okay, this is pancreatic beta cell excitation, but you see how it goes, and then we can actually scan CT scan image and create a three-dimensional model of the organ. And then we can actually create this very high definition visualization of the either the medical image or a simulation result. And then we can actually combine them together. Oops, okay, it doesn't really move. Okay, yeah. Okay, so you see this is an excitation pattern. This is electrophysiology of the heart result of this. This actually electrophysiology reflecting whole body ADME, and then what the cardiofibroblast and what is the mutation behind and this. And then also, there are software which actually do the pathway-wide high-definition docking simulation. So we can actually see a specific molecule, drug, may interact which molecule in the pathway. So there's a range of software that you can connect with. So we can actually do the drug interaction modeling and how that the specific mutations might impact and then how that it relates to the physiology. Okay. Now, second is a horizontal thing. How we connect the genomics and gene expression to patient monitoring and the network, through the network. For example, can you run the movie here? So this is an example of the expression pattern. For example, we got that from the database, and then how you can reconstruct and infer the possible regulatory network from the large-scale data. So this is the big data from all the expression profile. And there are a lot of inference methods we actually implement in everything available. And this is a consensus, the most probable regulatory relationship. And this is the most reliable one. You see, this is the most likely regulatory relationship inferred from the large data of the expression profile. Now, the other way around is a lot of papers published. This is a deep curation, is you read the paper and reconstruct the molecular interactions. So this is not from big data, but the big knowledge base. And you reconstruct the high precision data curations, knowledge curation, and create. This is the two-rack receptor pathway, which is like an immune system. And we read 1,500 paper in depth and create very precise and accurate map. And this is Alzheimer pathway. We read 2,000 papers on Alzheimer and related papers and create all the pathways, molecular interaction related to Alzheimer in precisions. From those data of the map and then also like algorithmic inferred one, we run specific algorithms to identify which node in the network may be important. And this is more the mathematical thing. So at the same time, this has a relatively accurate prediction of what node, what molecule could be important, the specific disease phenotype. And this is the case of Parkinson, but we can do an Alzheimer's and other disease. They combine them together. What we can do is run through the expression profile or a genome in the behind and infer the network and reconstruct the network and map it out. And do the mathematical analysis of what is the important molecules, and we can try to narrow down the highly likely biomarker, most important biomarker for the experimentally verifying. And this is the kind of pipeline that will actually be built on the software, built by the different institutions, but all comply with the Garuda. And this is another example how you got the age of onset trait analysis in Alzheimer. I have like a different data set, and then we actually infer the difference of the network for the different onset in a different region, cortical region, and you can actually visualize that. Now, particularly in the CNS or diabetes, you need to actually consistently monitor the patient behavior. Okay, this has been the weak part of the CNS research because you can do the sequencing, you can do the all sort of biochemical assay, but how you can track down the patient behavior in precision has been rather difficult. And I think you have a movie here? Or no, okay. Yeah, okay, thank you. Now, what you're actually looking at it, this is one of the sensor systems that we can actually sense the tremor, but this is infrared, but you can be the wearable or other mechanism. We can actually create the multiple sensors fusions. Now you can actually see the people's behavior, hand behavior, and seeing the tremor level. And if the tremor is high, you can actually alert this the doctor or patient directly. And so this is a connected device, a connected system with multiple devices and then into the biomedical system. And it's important part of this is this a wearable and a connected smart sensor system is compared with Garuda. That means that can be automatically linked with a molecular network analysis and genome analysis. Okay, so a lot of wearable system, but never integrated with the genome analysis or expression profile. This system enable the pipelining genome and expression profile, a lot of biomedical data, healthcare data, and patient behavior monitoring. So, and then, of course, we have a connection system that enable to interface with the mobile phone, which is a revolution, and we can actually use mobile phone to constantly monitor the patient or provide appropriate feedback. For example, one of the applications we have is if a patient is in a trouble and have high tremor level, we alert, or if a patient calendar actually have some schedule for going for the party, we can alert the patient, okay, please enjoy the party, but before going there, please take the pill. For example, that is actually one possible function we can have. Of course, all those processes have to be approved for the medical legitimacy, but functionally, technically, we can do that. So we actually have quite a bit of connections, how to learn automatic classification of cohort, and we are making a lot of discovery here as well. And so we actually now integrating health records, biomarkers predictions, and the sensor data into the Garuda platform. This is more the patient and clinical-oriented part of the Garuda. And remember that the system biology part, the simulation and genome analysis on the other side of the platform. So we actually trying to create the evolving cohort because this is a lot of anti-colony because every software can be built by us or by any one of the community, and we can actually integrate from the device to the NGS analysis, next generation sequencing analysis, the clinical database, to the very basic science of system biology. And we are trying to create not necessarily the top-notch at this moment, but the evolving cohort, evolving anti-colony, which is most important because in evolutions and the system ecology of the software is always the most interesting, the most cutting edge. And that is something we're creating. Now, we noticed that a lot of data have to be handled, and we will completely overwhelm. So we actually create a turnkey system, the Garuda terminal. The one of the reasons is our corporate partner requires not the downloading site, turnkey system because of security concern. So we actually had a high security dedicated system for we can actually provide turnkey. So like IT security people will be happy and they can sleep well. Now, so the platform being built, and now actually this is like a Saturn V or like a launch vehicle part, which is a software foundations, and it's a really standard platform, and that's there. And it's thankful quite a number of researchers and the medical institutions behind. So that's what they are doing. And then how do we set time? Is it about time? Or? Yeah, okay. So I think I'm going to stop now, and then this is my contribution for the community. Thank you very much.